last quiz we took. All right. The chapter we're going to talk about, or we're going to dive into, is the symmetric matrices. It's a chapter on symmetric matrices. And it turns out that symmetric matrices has a lot of really important properties, or we could take advantage of it and apply it to a lot of things. And the first thing we're going to take a look at is the diagonalization of symmetric matrices. And then we'll apply it to other things. We'll apply it to like a rotational transformation in 2 dimensions, or maybe even in 3 dimensions. And that all involves changing basis and stuff like that. And then our last topic would be another kind of decomposition, the singular value decomposition. So we'll learn about singular values. We'll also talk about the should call it the sign. So you know how numbers can be positive or negative or zero. Turns out matrices has a way to determine or identify a sign, and that phrase positive definite that we saw in the meme is one of those things. So we're going to talk about positive definites, and we're going to apply it to Calc 3. And for those people that haven't taken Calc 3, then don't worry too much about it. But if you're going to take it in the near future, then it might be a good thing to look at in detail. But we're going to apply it to the Jacobian. And, you know, Jacobian is the second derivative test says that the sign, whether it's positive or negative, tells you it's concave up or concave down. So there'll be something similar to this in 3 dimensions, where your paraboloid is either concave up or concave down, depending on the sign, quote, sign of your matrix, your second derivative. All right, so that's a quick overview, preview, and so let's dive into diagonalization. And for this, do you remember how to diagonalize a matrix? That was like an exam too, right? What's involved in diagonalizing a matrix? We need eigenvalues and eigenvectors. So let's take a look at the definition. We know what symmetric matrix is. Symmetric matrix is a matrix such that the transpose is equal to itself. So we have to make sure that we actually do have a square matrix. So we're going to restrict our study now to just square matrices that are symmetric. Its main diagonals can be whatever, but what's important is that if you fold this matrix along the diagonal, your numbers are going to match. That means your ijth term is the same as the jith term. So here's an example of a diagonal or a symmetric matrix. Oh, they want us to diagonalize it already. Do you remember how to do eigenvalues and eigenvectors? All right, let's try. I think I may have forgotten. I hope not. Right now, I'm teaching the class. I hope I didn't forget. Eigenvalues, lambda. Oh, remember lambda? So we're going to do lambda. A minus lambda I business, determinant. So the determinant, and then we want to 3 minus lambda, 2, 4, minus 2, 6 minus lambda, 2, 4, 2, and 3 minus lambda. So we want to find the determinant of that. Oh, you remember how to find the determinant? All these things are coming back to us. Yeah, so you cross out. Let's expand on, I guess it doesn't matter what we expand on. There's no zeros. That's not going to help us. So let's just expand on the first row. So we have 3 minus lambda, and then determinant of what's left, 6 minus lambda, 2, 2, 3 minus lambda. Then alternating, right? Positive, negative. So it's negative 2, and then 2, 2, 4, 3 minus lambda. And then a 4, minus 2, 6 minus lambda, 4, 2. Do you guys have a way to find eigenvalues in your calculators? No. Yeah. Yep. All right, so now this is going to be a big 3 polynomial, 3 minus lambda, 6 minus lambda, 3 minus lambda, minus 4, plus 2 times negative 2 times 3 minus lambda, minus 8, plus 4 times negative 4 minus 4 times 6 minus lambda. Wow, that's a lot. Just might as well distribute this. This is going to be lambda squared minus minus. It's a 9 lambda plus 18. So this is lambda squared minus 9 lambda. What? Plus 14? Plus 2 times, can we do this? Minus 6 minus 2 lambda minus 8. What? Plus 2. Okay, so 2 lambda minus 14 plus this is going to be negative 4 minus 24 plus lambda. So 4 times lambda minus 28. Oh man, this is long. So 3 lambda squared minus 27 lambda plus 42 minus lambda cubed plus 9 lambda squared minus 14 lambda plus 4 lambda minus 28 plus 4 lambda minus 80, 102. Huh. Yeah, yeah. Minus 4. This one? Up. Up here? Shoot. Remember back in algebra and we had to do all this multiplying and keep asking yourselves when will we ever use this? Should have paid attention back then, huh? All right. Let's see what happens. A few people got the answers already. Let's see if we can match up with their answers. I'll keep the negative here. The squared terms. There's only one squared term. I guess there's 2 squared terms. That would be 12. 1, 2, 3, 3, 3. Oh, now we have to add all that. 10, 6, 6, negative 21, maybe? And then constant terms. 130, 140, negative 140, 98. I hope. I should just have Wolfram find the answer for us, right? Okay. Hope this is right. I wonder, 98 is 7. 7's divisible by that, right? There's a 21. Let's see if 7 would work. Let's change the signs. Let's make it all positive. Or just make the first one positive. So my guess is 7. You guys remember, what's that called? Long or synthetic? So multiply by 7, add, is it negative 5? 7 is 35, negative, this is going to be 14 times 7, 98. Oh, nice. So we know this is lambda squared minus 5 lambda plus 14. Is that factor? Lambda 7. Would that work? 7 and 2. Yeah. What was your answer? 7, 7, and what? Negative 2. So this is this is a minus. Whoa. So plus 2, negative 7. So then you have lambda minus 7 is, so this is, those are your eigenvalues, 7, 7, and 2. Negative 2. 7, 7, negative 2. All right. So for each one, we have to find the eigenvector. You know how to do that? So let's do negative 2 first. So lambda is equal to negative 2. Then your matrix up here, I have to subtract negative 2. So I have to add 2 to all the diagonal entries. So this is 5, 8, and 5. And then minus 2, 4, 2. So we want to row reduce. Oh boy. Maybe I'll switch the first row and the second row, and then at the same time multiply that by 1/2, negative 1/2, to make it positive. Five, negative 2, 4, 4, 2, 5. So we did is row 1 and row 2 switched, and then we took this row, either before we switch it or after we switch it, multiply it by negative 1/2. All right, so now I can eliminate the first entries in the second row and the third row. So I have the first row stays the same. So this becomes 0. So -5 times -4, positive 20. 20 minus 2 is 18. Okay. One. 1/2. All right. So this is good. That means we have a one-dimensional null space. We have one free variable. And so our free variable, this is x. Our free variable is going to be represented by 1. And then we got this thing. What do? We take the negative of it, right? Negative 1/2 and positive -1. And so we could scale that to something that we would be nicer to deal with. So maybe V1 or V that corresponds to the eigenvalue of -2 is going to be, let's multiply it by 2. So -2, -1, and +2. Okay. All right. So now with this next one, we're hoping to get a null space that's two-dimensional because this has multiplicity 2. If we get it to be two-dimensional, then we could say, yes, it's diagonalizable, it'll work. If it doesn't, then it's not diagonalizable. It turns out that there's a theorem that we'll see later on that symmetric matrices are diagonalizable. So I hope we get something two-dimensional here. We're going to subtract 7 to the diagonals. That would be 3 minus 7, -4. What was this before? 6 minus 7, -1, and -4 again. All right, can you guys REF that so we don't have to? I'm hoping we get 2 rows of zeros, right? We'll see. What do you guys get? So what's on top? 1, 1/2. All right. So the 2 rows of zeros says that we have 2 pivot or 2 free variables and 1 pivot. So we're going to get our free, and so x1 is going to be -1/2 x2 plus x3, and so that breaks up to how does it break up to? Yeah, I forgot how. Oh, so your vector is going to be -1/2 x2 plus x3, x2, and x3. That's it. So this breaks up into 1/2 1 and 0 times x2 plus 1, 0, and 1 x3. Yeah. Yeah. So that's good. The eigenspace for lambda is equal to 7 is two-dimensional. And so the basis for that would be these two. So x, let's call it v, v2. And then I'll multiply this by negative, or I'll multiply this by 2 so that I'll have nicer numbers. So that's negative 1, 2, 0. And then v3. Oh, that one's already nice whole numbers. So those are the vectors that span the eigenspace for this. So how do you do the diagonalization again? Put them into the matrix. So the diagonal 7, 7, negative 2, and what goes here? Wait, which one? I probably want to put because this is 7, right? So I probably want to put one of these two vectors first. Do we? Do we? Should we? Are they? What? You have to normalize the eigenvectors? We have to do all that? So we're not done yet? Bummer. Oh, well, can you just eyeball it to see if they're orthogonal? Are they? Okay, so it's going to turn out that, well, first of all, they don't have to be orthogonal for us to diagonalize the matrix, right? In fact, they don't have to be orthonormal for us to diagonalize the matrix. But if you have a symmetric matrix, it turns out that they're going to be orthogonal. Well, if you call this V1, then V1 dotted with V2 is equal to 0, and V1 dotted with V3 is equal to 0. Guaranteed if they're symmetric. Now, V2 and V3 are from the same eigenspace. They may not be symmetric. So we have to be careful about that. In this case, I think if we dot them, I get negative 1, 0, and 0. So they're not symmetric. Or they're not symmetric. Sorry, they're not orthogonal. So V1 dotted with V2 is not equal to 0 in this case. Right? But by the Gram-Schmidt process, we can make those two things orthogonal. Remember how to do that? So we can make them orthogonal, and so we can create orthogonal basis. By the way, this P, if I find P inverse, it should work. But there's something more to be said if you have symmetric matrices. The fact is that if you have eigenvectors from the different eigenspaces, then those are going to be orthogonal. The eigenspaces will be orthogonal. Within the eigenspace, though, they might not be, so we have to be careful. Thomas, and then we'll get to you. This is only for symmetric matrices. Yeah. Space. Yeah. So not just each, I mean, they're orthogonal to each of the eigenvectors, but they're actually, actually orthogonal to the whole space that's spanned by V2 and V3. Within the space, the two vectors may not be orthogonal. Does that idea make sense? So now, if we want an orthonormal basis, which is what we're going to strive for here, we're going to want to make sure that we do the orthogonalization. So I'll pick this as my V1 or U1, and then let's project U1 or V2 onto V3. So let's call this U1 is equal to 1, 0, 1. And so U2 is going to be V2 minus V2 dotted with U1 divided by U1 dotted with U1. So what is that? I don't know. That's minus 1, 2, 0, minus, and then the dot product between these two, that's negative 1, 0, 0. Dot product of U1 with itself is 2. And then multiply by U1, 1, 0, 0. So U2 is equal to, what is it? Negative a half, 2, and 0. Oh, this should be 1. Negative a half, 2, and positive a half. Wow. And now we just need to normalize all those. And we have our matrix. So normalize U1 divided by the length, which is root 2. So that's 1 over root 2, 0, 1 over root 2. The next one, this is harder to normalize, but I'm going to do the last one. 4 plus 1 is 5, plus 4 is 9, so that's 3. Negative 2/3, negative 1/3, and 2/3. And then whatever the normal of this is. Anybody guess what the normal of this is? Anybody? I like to deal with whole numbers, so if we scale this, negative 1 multiplied times 2, multiplied times 2, and then the 16, 17, 18, square root of 18. Then that would be it. Wow, that was rough. But now P is actually an orthonormal matrix. It has orthogonal and unit length column vectors. That was a pretty tough first problem to do. Any questions? Are you guys comfortable with the grunt work that's happening? So can I just use Mathematica to figure out the eigenspaces? Because I don't want to do this again in class. But you should be able to do it, right, on the test. I don't know what's going to be on the test. Who knows? So let's throw some theory out here. There's a theorem that says if you have a symmetric matrix and any two eigenvectors that are different, they're distinct, that come from two different eigenspaces, we'll have orthogonal eigenspaces. We saw that. And here's a quick one-line proof, one line with a bunch of equal signs. It says if you take any two vectors and then you multiply it by the one of the eigenvectors, somewhere along the line, you're going to say this is going to be equal to those same two vectors dotted with a different eigenvector. And the only way these two will be equal to each other, lambda 1 v1 dotted with v2 equals lambda 2 v1 dotted with v2, would mean that v1 and v2 are the same vectors or the same values, and so lambda 1 equals lambda 2, which is a contradiction. Because we said in the beginning of the proof that lambda 1 and lambda 2 are distinct eigenvalues. And so this is a short proof called the proof by contradiction. You assume something that you're thinking that it's probably not right. So you assume this fact, and then you work out some information, and then you come up with a contradiction in the end and say, oh, my assumption must have been wrong. And so that's how they show that. All right, so that's interesting. We saw that in our super hard example. It wasn't super hard, was it? It was just regular hard. Another theorem or definition. We talked about orthogonally diagonalizable already, right? This is just to show that it's orthogonally diagonalizable if your P matrices are orthogonal, orthonormal matrices. So a special type of diagonalization is said to be orthogonally diagonalizable if the orthogonal matrix P and the diagonal D such that this is going to be true. So such diagonalization requires the same amount of linearly independent orthonormal eigenvectors, which we're able to find. And then a theorem that follows after that is if you have an orthogonally diagonalizable matrix, then your matrix must have been symmetric. Or vice versa, if your matrix is symmetric, then you're guaranteed to have an orthogonally diagonalizable matrix. Oh, these words are hard to say. Okay, so again, that's something that we saw already. I think I might have another example here. All right. Oh, apparently I did the example already, so let's get the example in our notes and walk through it so I don't have to do it by hand. This is a 2 by 2, so it should be easier, right? So your example is your matrix A is 3, 1, 1, 3. It's symmetric. And so according to the theorem, you're guaranteed to have an orthogonally diagonalizable matrix. Not only that, that if you take your eigenvalues, you should have two distinct eigenvalues, and those eigenvectors for those two distinct eigenvalues will be perpendicular. So we first found the eigenvalues. Eigenvalues turned out to be 2 and 4. And then to find the eigenvector, you find the eigenvector for 2. I got -1, +1, but let's normalize it so that it's -1 over root 2, +1 over root 2. And then we did the same thing for eigenvalue 4. And then my eigenvector was 1, 1. Again, we normalize that, so that's 1 over root 2, 1 over root 2. And then you put that in a matrix, and this is your P, and your diagonal is 2, 4. And you just have to make sure that if the first entry your diagonal is 2, then you have to make sure that the first column in your P matrix is the eigenvector for that eigenvalue. Okay. All right, why don't you try one? Uh, 3, 4, 4, 9. Go ahead and try it. Let's give you 5 minutes to work on it. And we'll check up on you. All those people that were on their computers, oh shit, now what am I gonna do? I hadn't been paying attention. What's this? How do you do this? All right, let's diagonalize this matrix. 3, 4, 4, 9. Oh, example. So basic steps, find the eigenvector, find the eigenvalue, and then if you want to check, you can check to make sure that the two eigenvectors from the different eigenspaces are perpendicular, orthogonal, which they should be, and just normalize it, and then you're good. 3, 4, 4, 9. Should pause this. All right, so if you just follow through the process, I think in a test situation, I should only give you a 2 by 2 matrix. Otherwise, a 3 by 3 matrix. I mean, even if you do it with a calculator, it still could be a little tricky to find the solutions and stuff. So 2 by 2 matrix should be fine. Yeah. Well, if your answer is equivalent to mine, what's your answer? I don't think this is a unit vector, right? If you work that out, it's not going to be a unit vector. So if you make it into a unit vector, then you'll get the same answer that I have. It looks like it's the same direction as my vector. It's scaled the same, but it's scaled differently. It's the same direction vector. Like if I multiply this by root 5 and then divide by 2, I'm going to get 1, 2, which is the same vector that we were talking about, except this is not a unit vector. Okay? Any other questions? So we're good. So now we know that symmetric matrices are orthogonally diagonalizable. And we can find the diagonalization using eigenvectors and eigenvalues. So decomposition, there's a spectral theorem and a spectral decomposition that we're going to talk about. So the spectral theorem tells us a bunch more facts about symmetric matrices. And these are, if you have a symmetric matrix, then here are a couple of facts about them. A has n real eigenvalues counting multiplicity. So we should expect all the eigenvalues to be there. The dimension of the eigenspaces for each eigenvalue equals the multiplicity as a root of the characteristic equation. Another way to state that in the language or in the vocabulary that we've been using is that the algebraic multiplicity is the same as the geometric multiplicity. So in our first example, when we got 7, 7, negative 2, 7 had algebraic multiplicity 2, and when we found the eigenvectors, we found a two-dimensional eigenspace, which is what we need to expect. Remember, sometimes we have algebraic multiplicity 2, but we only got one eigenvector out of that. So that's not going to happen if you have symmetric matrices. C, the eigenspaces are mutually orthogonal in the sense that eigenvectors corresponding to the different eigenvalues are orthogonal. Now again, within the eigenspace for one eigenvalue, those two vectors may not be orthogonal, as what we saw in our first example. With the eigenvalue of 7, we had two eigenvectors, but they were not orthogonal. However, by the Gram-Schmidt process, we can make them orthogonal, and therefore they are orthogonally diagonalizable. Okay? So spectral theorem talks about the spectrum. And when they talk about spectrums for matrices, they're really referring to the eigenvalues. Eigenvalues are special numbers, remember? Did we ever establish what that means in German? That's a German name. Eigen. It's what? Self. So the eigenvalue are essentially like special numbers that describe the matrix. And the spectral theorem kind of displays that. So what is a spectral theorem? Or spectral decomposition? Whenever we talk about decomposition, remember it's like rewriting the matrix into, ooh, it's not going to fit. Let's put it on a new page. Sorry. So whenever we talk about decomposition, we're talking about rewriting your matrix as a product or a sum or whatever. In this case, it's a linear combination of things. But the idea is that if you have a symmetric matrix, then it's orthogonally diagonalizable, and we can find an orthonormal basis for each of the eigenvalues. And so what they're saying here is that you can write, this is the decomposition right here, you can write your matrix as the eigenvalue times some other matrix plus the second eigenvalue times some other matrix times the third eigenvalue times some other matrix, etc. And what are those matrices? Those matrices are these expressions. Trying to highlight this. There we go. Well, without the plus sign. U1 dotted with U1 transpose. Isn't that just dotted with itself? Isn't this the dot product? Isn't this the inner product? Are you sure? This looks like a dot product, right? Wait, what? So if you have a vector u, u transpose times u is the inner product, also known as a dot product. What if you switch them? U times u transpose. So that becomes a square matrix. And remember, we kind of called it the outer product, opposite from the inner product. So the inner product is like a dot product and you get a scalar. The outer product, you actually get a matrix. And so what you're saying here is that you can rewrite your matrix as a linear combination of matrices, right? And your constants are going to be your eigenvalues, and your matrices are going to be the outer products of the corresponding eigenvectors. What? All right. Let's take a look at an example. Well, let's take a look at the simple example. Well, not simple. The example that you guys worked on. So this is what we have, right? And so let's rewrite that according to eigenvalues and eigenvectors. And so what we're saying here, according to this, is let's say lambda 1 is equal to 1, and u1 is the vector corresponding to lambda 1 is what? Negative 2 over root 5, 1 over root 5. Okay? And then lambda 2 is 11, and u2 is going to be 1 over root 5, 2 over root 5. Okay? So what they're saying now is that if I take u1 inner product with u1 transpose, I guess I should use t, this is going to be u1 minus 2 root 5, 1 over root 5 times minus 2 root 5, 1 over root 5. What is that? How do you do this multiplication? It's row and column, so it's negative 2 times negative 2, that's positive 4. Root 5 times root 5. You multiply that, right? Multiply the denominator, so that's 5. Negative 2/5. Negative 2/5. 1/5. Right? And then u2 dotted with u2 transpose is going to be 1 over root 5, 2 over root 5, 1 over root 5, 2 over root 5. So that's 1/5, 2/5, 2/5, 4/5. So what they're saying is that if you take your first eigenvalue and you multiply with this new matrix that we found, 4/5 minus 2/5 minus 2/5 and 1/5, and add your second eigenvalue and the second outer product, you should get, well, let's work it out. Yeah. For one eigenvalue, then you would just say this eigenvalue with the first eigenvector, and then the same eigenvalue with the second eigenvector, and then continue on. So let's actually see if we can find this. So this is 1 times the matrices for Mathematica is written a little bit differently. 4/5 minus 2/5 minus 2/5 1/5 plus 11 times 1/5 2/5 and 2/5. Have you guys heard of that? The 1/5 2/5 red fifth blue fifth? I have a meme for that. It's in the mug. Anyways. Oh, I should put this in matrix form. Oh, come on, matrix from form. So we get the same matrix as we started off with. So the spectral theorem allows you to write your matrix as a linear combination where you're using the eigenvalues as the constants and the eigenvectors as the outer product of the, it has to be a unit vector, the corresponding unit eigenvectors. That's a lot. Spectral theorem. Any questions? Yes. Well, at this point, we can say that this is used to help us to display, essentially display the eigenvalues. It allows us to break this up into eigenvalues. It could be. Speaking of art, we're going to take a look at some image processing towards the end of the semester too. And it's dependent on the number of eigenvalues your matrix has. What? Computer science. Whoa, this is kind of cool. All right, so if you see a symmetric matrix, then you know that it's orthogonally diagonalizable, and then you can do the spectral decomposition for it. Yeah. Spectral? It's what? I don't know if it'll give you that much information because you're taking your eigenvectors and then you're taking the outer product of that, so you're making a matrix out of it. And I don't know if you would get a direction from the matrix. But you get to use your eigenvalues as the constants, as the weights of the matrices. Yeah, it tells you how much your matrix is being scaled, whatever that means. Yeah. Of course, it might mean something when you're doing some sort of engineering problem later on in the future and then your boss tells you to use a spectral theorem. And you say, oh, okay. And then you'll remember 1/5, 2/5, red fifth, blue fifth. inverse? Nothing. If P, and in this case we want P to be an orthonormal matrix. If P is an orthonormal matrix, then the inverse and the transpose are the same thing. Which means now if we got an orthonormal matrix, we even know the inverse of that. Just take the transpose, and then that's it. Okay. All right. There's a lot to swallow. We have, we're going to keep punching through chapter 7. So I'll probably give you a quiz on Monday. unless I make it too hard and then I said, oh, crap. Yeah. 7-4 is our goal. Yeah.